Hello everyone, this is section 6.2 over anti-differentiation by substitution. In example 1, this is an indefinite integral, meaning there are no boundaries here. We're not integrating from -1 to 2, we're just doing the integral. So when you have an indefinite integral, you do the antiderivative, and then at the end, you just have to remember plus c. So the antiderivative of this function that's given in example 1 is 1/3 x to the third. We bump the power up 1, and of course we have to have the 1/3 so that when we would take the derivative, we'd get 1 in front, plus cosine x, and then plus c. In example 3, we are asked to pay attention to the differential. And the differential in this case is the dx. The differential here is du, and the differential in the third one is dx given. We are asked to let f of x equal x to the third plus 1 and let u equal x squared. And we're going to find the following antiderivatives and, of course, pay attention to the differential. In letter A, we are asked to find the antiderivative of f of x with respect to x. So there's really not much to do other than take the antiderivative, which is 1/4 x to the fourth plus x plus c. In the second one, we're asked to find the antiderivative of f of u with respect to u. So in this case, f of u is u in place of the x. So we'll have, instead of x to the third plus 1, we have u to the third plus 1. If we take the antiderivative of this with respect to u, it's 1/4 u to the fourth plus u plus c, and of course u is x squared. So any place we see a u, we're going to put an x squared. So simplifying, we get 1/4 x to the eighth plus x squared plus c. In the last one, we're asked to take the antiderivative of f of u with respect to x. In this case, we're going to replace x with x squared with the u. But since we're taking the antiderivative with respect to x, that's why we have to make this substitution in right away. And in letter B, we didn't have to do that. So in letter C, we substitute x squared in for x. So we get x squared to the third from the first equation here, from f of x, and then plus 1. So the antiderivative is 1/7 x to the seventh plus x plus c, because this x squared to the third is x to the sixth. That's why we have a 7 here. In example 4, we are asked to take the antiderivative of sine of x, e to the cosine of x dx. And we're going to do that using substitution. We're going to let u equal the cosine of x, or the exponent of e, so that when we take the derivative of u, we get negative sine x dx. And we have a sine x dx in the original problem, so we can make a couple substitutions. First of all, we can replace cosine of x with u, and that here, and we can replace sine x dx with actually negative du if we divide both sides by negative. So sine x dx becomes the negative du. And I've put the negative out in front of the integral. Now when we take the integral of e to the u, it's e to the u. We bring that negative with. Now we didn't start with a u, so we can't end with the u. The answer is negative e to the cosine of x, and of course we need a plus c because it's an indefinite integral. And there's example 4. In example 5, we're going to do almost exactly the same thing. We have this antiderivative here, and we want to let u equal as much as we possibly can. In this case, we can let u equal 5 plus 2x to the third, so that when we take the derivative of both sides, we have the derivative of u equals, well, the derivative of 5 is 0, it goes away. Derivative of 2x to the third is 6x squared dx. Now we're doing this derivative implicitly, that's why we have du and dx on both sides. Well, in the original antiderivative, or the original integral, I have an x squared and a dx, just like I have here, but I don't have this 6x squared. So I'll divide both sides by 6. So we're going to replace x squared dx which is actually in the original integral, we're going to replace that with 1/6 du instead of just du. Well, when we do that, here's what we get. 1/6 is on the outside, u is under the radical, and we know what the antiderivative of the radical is. It's u to the 3/2 times 2/3, and the 1/6 just kind of follows it along, and then we have plus c. Well, when we simplify a little bit, we get 1/9. 2/6 becomes 1/3. 1/3 times a third is 1/9. And we didn't start with u's, so we can't end with u's. So u is replaced with 5 plus 2x to the third. And there's your answer. And of course, we have the plus c again. In example 6, we are asked to evaluate the cosine of 7x dx. Well, we know what the derivative of cotangent, I know I said cosine before, it's cotangent. The derivative of cotangent is negative cosecant squared, but we're not taking the derivative, we're taking the antiderivative. And we don't know what we take the derivative of to get cotangent. So we're going to have to manipulate this function a little bit. We can write cotangent of 7x as cosine over sine, with the 7x, of course. In this case, we want to let the u equal the sine of 7x, and then take the derivative of both sides. Derivative of u is du. The derivative of sine of 7x is 7 cosine of 7x dx. Well, I have the cosine 7x dx, but I don't have the 7, so right now we can't make the replacement, or the substitution, that is. But if we divide both sides by 7, I do have exactly what's in the original integral, which is cosine of 7x dx. Now, the sine of 7x can be replaced with u, and the cosine 7x dx can be replaced with 1/7 du. And that's what I have in this first statement here. The antiderivative of 1 over u is the natural log of the absolute value of u. And the reason we need absolute value of u is because you can't take the natural log of a negative number. And you can't take the natural log of 0 either. So we have 1/7 natural log of absolute value of u plus c. Now, we didn't start with u's. There's no u's in the original problem. We can't end with u's. So we're going to replace the u with sine of 7x. And then, of course, we have the plus c. In example 7, we are setting up a substitution with the trigonometric identity. So we're given an integral, and then we're going to manipulate it using one of the identities that we learned in trigonometry. The first one, letter A, it's dx over cosine squared of 2x. We're not going to use the substitution right away. Rather, we are going to make 1 over cosine squared into secant squared of 2x. We're going to let u equal 2x, so that the derivative is 2 dx. Well, I don't have a 2 dx, so we divide. There's no 2 dx in the original integral. We divide by 2, we have 1/2 du, and the dx is replaced with 1/2 du, and I will replace the 2x with the u. We do know what we take the derivative of to get secant squared. It's tangent, and the 1/2 kind of just comes along with it. We have plus c, and in the end we have 1/2 of tangent of 2x, so we replace the u with the 2x. Once again, we didn't start with u's. We can't end our problem with u's either. In letter B, the cotangent squared of 3x is cosecant squared 3x minus 1 from the Pythagorean identities. I can let u equal 3x, so du is 3 dx. We don't have a 3 dx in the problem, so we divide by 3. 1/3 du equals dx. Making the substitutions, the 3x becomes the u, and I have the 1/3 du. Here's the antiderivative. We replace the u's with 3x, and we have it. I got to limit these to 10 minutes, so I think this one is going to have a part 2.